Hello everybody, welcome back to another video. Today we're going to be looking at the May-June grade 12 question paper 2, that is the year 2024. Alright, so this is question number 8, which from here going downwards we're dealing mostly with your circle geometry as well as your proportionality theorems. Alright, but today we're looking at question 8. The statement reads as follows. In the diagram, chords AB, BC, and AC are drawn in the circle with a center O. So we're looking at the statement, and here's the drawing. There's AB, AC, and BC. They are drawn inside of this circle. There's O that we're given, and DCE is a tangent to the circle at point C. There is our DCE. It is a tangent at the circle at that point C. Now the question is asking us to prove the theorem which states that the angle between the tangent to a circle and the chord drawn from the point of contact is equal to the angle in the alternate segment, i.e. BCE equals to A. Right, let's try draw BCE. Okay. So they're asking us to prove that BCE, so this angle here, BCE is equal to the angle A. All right. That is the Tan-Chord theorem. So there are lots of ways that one can go about this, but I think this is the easiest, straightforward solution. We're going to do constructions here strategically to make our solving of this question easily, and also are going to introduce a couple of variables just to make sure that we discipline the question. All right, so if you construct two radius already at this point, so if we look at point C to A, if you construct a radius here, radius OC, construct radius OC and OB. All right, first step. Now the second step is that we are going to let the angle OCB, so this angle here, and angle OBC. So we're going to let OCB to be equal to X. I'm going to let OBC to be equal to Y. So let OCB equals to X and OBC equals to Y. All right. So we have two new angles here. Not really new, but two new variables. There is angle X and there's angle Y. All right. So what we can know from here is that we have two radii which are closing off this nice triangle here. So if you look at the triangle, this is our triangle. What is the triangle that has two equal sides? That is an isosceles triangle, and we know that the base angles of an isosceles triangle are equal. So which means here angle X must be equal to angle Y, right? But angle X is equal to angle Y. The reason is that these are base angles of isosceles triangle. That triangle is triangle OCB. All right. So we have two angles here that are equal. So you can write your Y to be terms of X. All right. So when we're done with this, we can find the angle BOC. Find angle BOC. So BOC plus this angle and this angle. So BOC plus X plus Y, this should all give you 180 degrees, because these are angles of a triangle. They all add up to 180 degrees. Right. Therefore, your angle BOC is equal to 180 degrees. Subtract your x, subtract your y, but we know that y is also equal to x. This is going to be equal to 180 minus 2x. Alright, now that you have BOC, we are trying to still link the angle BCE to angle A. So how can we find the value of A to also be in terms of that x? And note that we haven't linked BCE to x, but we're still trying to solve angle A now. But if you ask yourself, where is angle A? Angle A is at the circumference. It is enclosed by the chords AC and PA. Alright, what do we know about an angle at the circumference? Someone may say that there is a theorem that says an angle at center is twice the angle at the circumference. Another person may say that there's a theorem that says angles subtended by the same chord or angles in the same segment. Alright, but in this drawing here, we must focus on the first theorem, which is the angle at center is twice the angle at circumference. So we can already tell from here that angle BOC is equal to 2 times angle CAB, right? Or angle A. This is because angle at center is 2 times angle at circumference.
And 2A.
Or 2A. Alright. Now, to find the angle A, we have to say A is equal to BOC divided by 2. And what is BOC? BOC is 180 minus 2x. 180 minus 2x divided by 2. This is the same as saying 180 divided by 2 minus 2x divided by 2. This is going to give you that angle A is equal to 90 minus x. Right. So we found the value of angle A is 90 minus x. Now let's go back to the first angle, because we're still trying to prove that this angle is equal to this one. We have found what this one is in terms of the variable that we created. Now let's look at this one. Where is this angle BCE? Here. It is between a chord and a tangent. Alright. But one thing we must also note is that it's also between, we can see that in between this angle, there's an angle here and then there's x, which is sort of, so angle BCE plus x are making the angle formed by the radius and the tangent. And what do we know about the radius and the tangent? Wherever those two meet, that will be a perpendicular intersection. Alright, so we already know that OCE is equal to 90 degrees, right? And this is because this is a red perpendicular to tangent theorem. I like it when you note which radius you're talking about. The radius we're referring to here is radius OC, and the tangent we're referring to here is tangent DE, or you can say it's DCE. Alright, now what makes up OCE? OCE is made out of the angle X and the angle that we're looking for, which is BCE. Okay, so this is going to be your BCE plus the angle X. These make up 90 degrees. To solve for BCE, we make it the subject of the formula, so this is going to be 90 minus X. So we found that BCE is 90 minus X. Remember that we also said A is equal to 90 minus X. Therefore, BCE is equal to angle A. Right, we have just proven the tangent or the Tan-Chord theorem. Okay, now we're going to move to the next question, 8.2. This was question 8.1. Okay, now we're going to look at question number 8.2. The statement reads as follows. In the diagram, PQRS is a cyclic quadrilateral with RQ equals to RS. Here's the diagram. They are saying that PQRS is a cyclic quad, and they are given, and it is also given that SR is equal to QR. All right. Now there's a tangent which is called ST, that is a tangential at the like to the circle at point S. SR is produced to N. Where is SR? So SR doesn't stop here, it continues to the point N. Alright. And we're given that the angle R2 is equal to 68 degrees. Okay. The first question is determine with the reasons the size of, first question, angle P. So we need to find angle P. Alright. 8.2.1 must find the angle P. What is angle P? Okay. So every time I solve these questions, I ask myself, first thing you need to do is this angle that we're referring to, where is it located? 1, what is it surrounded by? 2, and because of its location, what other theorems or what theorems relate to something like that? So if we look at P, P is located at the circumference, okay? And then it is enclosed by 2 chords. There is a chord here, PQ, and there's a chord SP. There's also like a subtending chord, which is SQ, all right? That makes up this angle, all right? Now, it is an angle at the circumference. So first thing one can think about is angular center is twice the angle at the circumference. That's the first theorem, okay? But now, what is special about this P is that even though it is enclosed by SPQ, it also falls in a cyclic quad. It is one of the vertices, right? It is one of the angles in the vertices of the cyclic quad. So if you look here, this angle and this angle are all angles in a cyclic quad. This sign here doesn't mean that these angles are equal, okay? So we've included a second theorem there, that this is an angle in a cyclic quad, okay? So the first thing I said that an angle at center is twice the angle at the circumference. We don't have any angle at the center here. We're not even given the center. So we can chuck that one out. We're left with the cyclic quad. Now, in the cyclic quad, there's various tools we're given there, which is that the opposite angles of a cyclic quad are supplementary. The next thing is that the exterior angle of a cyclic quad is equal to the opposite interior angle and the cyclic quad. Which one can we go with here? We see that for us to find P using the first theorem, which is opposite angles of a cyclic quad are supplementary, we first need to calculate R1. Alternatively, is that an angle, the opposite angle, or let's say exterior angle of a cyclic quad is equal to the opposite interior angle in that same cyclic quad. And we do have that the exterior angle is R2, which is equal to 68 degrees. So we can already find P, that P is equal to angle R2 is equal to 68 degrees. Reason, exterior angle of cyclic quad. You can finish it. So exterior angle of a cyclic quad is equal to the opposite interior angle of that cyclic quad. Okay, we have solved for angle P. Now the next question is asking us to solve angle Q1. Angle Q1. Same procedure. Where is Q1? Q1, I can say it is at the circumference, but this is special that Q is split into two, Q2 and Q1. So Q1 now makes it to be in between S and RQ. So SQ and RQ. Okay. Now, what is special about these lines is that we were told that RQ is equal to RS. Okay. RQ is equal to RS. So first thing we have here is that we have an angle like this. If you can flip this drawing around, you have something like this. Right. We have an angle this is your S, and this is your Q, and this is your R. Okay, so we have here R2 and there's R1 here. All right, so this angle that we're looking for, which is no, so this is going to be your S, this is going to be your Q. We're looking for this angle Q1. There's also S2 here. Okay, now I told you that this angle is in a triangle, or this angle is sort of enclosed by QR and RS, and we know that RS is equal to QR. Okay, now what theorems link us to this? We know that we have a triangle, a special triangle here, which has two equal sides. And what is that triangle? That is an isosceles triangle. And what do we know about such a triangle? The base angles of that triangle must be equal. Okay, so we already know we have that into our toolbox. But now we don't even have this angle here. We don't have this one, we don't have this one. So we need to find this one first and then calculate this one. But there's another tool that we've learned a long time ago, probably grade 8, that an exterior angle of a triangle is equal to the summation of the two opposite interior angles of that triangle. Right? Exterior angle of a triangle is equal to the summation of these two angles. So let's start there. We are saying that Q1 is equal to angle S2. These are base angles of isosceles triangle. What is that triangle? Is QRS. Alright. But now we remember that an exterior angle we should have the value of, it is equal to 68 degrees. R2 is equal to Q1 plus S2. And the reason is that there is an exterior angle of a triangle is equal to opposite, so it's summation of opposite interior angles. All right, and we've just mentioned that Q1 and S2 are one of the same things, so we can say that Q1 plus Q1, which is Q1 plus Q1, should be equal to the angle 68 degrees. Q1 plus Q1 is equal to 2 Q1s. So 2 Q1 is equal to 68 degrees, and Q1 is therefore equal to 68 divided by 2, and this is equal to 34. That is equal to 34 degrees. Okay. Now let's move to question 8.2.3. 8.2.3 is asking us to solve for angle S1. Okay, angle S1. So same thing, where is S1? S1 is between a tangent ST and the chord SR. Need I say more? Between a tangent and a chord S1. In the previous questions we just proved a theorem that links a tangent and a chord. Okay, so we know that, and a first theorem that should come into our mind when we look at something like that is a Tan-Chord theorem. But that shouldn't limit us to think of other solutions. But that should be the number one. Now, that theorem says that the angle between the tangent and the chord is equal to the interior, so it's equal to the interior angle of opposite interior angle of that subtended by that very same chord. So if you have that chord, we're saying that this angle is equal to the opposite interior angle that is subtended by that very same chord, the chord that this angle is between it and the tangent. Okay, or exactly like how it is stated in the previous question, which is an angle in another segment, which is there's two segments here, so we're referring to that angle. Okay, now what is that in this circumstance? We have S1, and if you look at the triangle here, triangle of interest, it is this one. Okay, and what is the opposite interior angle that is subtended by that very same chord? This is angle Q1. Okay, so we can here straight up say S1 is equal to Q1. This is tan. What is the tangent? Tangent ST. Tan-Chord. What is the chord? Chord SR. Tan-Chord theorem. It is very important to note which chord or which tangent you're referring to. In this case, we only have one tangent, but we have many chords. So in order for us to know that you know what you're talking about, you know what chord you're referring to, please name that chord. Doesn't mean you'll get it wrong if you don't know, but I might doubt that if you know the chord that you're referring to. Okay. Now, what is the value of Q1? We've just calculated Q1 here. So S1 is the same as Q1, which is 34 degrees. Okay, that marks the end of our question number 8. If you have any questions, please leave them in the comment section. And yet again, please give us a thumbs up, a subscribe, and refer the video to more people. Thank you.